To resume, in the previous recording, I set up a thought experiment where we had a wire that was carrying what I referred to as a source current that flowed in this direction. And I suggested that the experimental evidence with the compass implied that the magnetic field that this current creates points in a direction perpendicular to the direction of the current flow, but not toward or away from the wire. And so that left either coming out of the board or going into the board. And again, oops, sorry, there was a little glitch on my computer there. I'm not sure what happened. Hopefully we're still recording. Yeah, okay. Anyway, the experimental evidence makes it clear that the magnetic field created by this current on the right-hand side of the wire in this particular drawing, the magnetic field points into the board, but over on the left-hand side, the magnetic field points out of the board. Now, we do not at this time, or there's nothing I have said that suggests why those particular directions. This and frankly all the other stuff that I said earlier about the magnetic field being created only by moving currents, magnetic fields being created only by moving charges, in other words, currents. Only currents can be affected by magnetic forces. So motionless charges cannot experience a magnetic force. All of these things, as well as these directions of magnetic field vector that I've drawn here, are results of experiments. Okay, so these are indisputable. We don't yet know why the magnetic field vectors point the way that they do, but the experiments show that they do, whether we understand why or not. So there's that. And then what we had is I had a positive charge cube that was moving through the magnetic field, the velocity v like that, and experimentally we discovered that a force appeared on it that pointed this way on the right-hand side of the wire. If the charge Q were on the left-hand side of the charge, it would still be attracted to the wire, but that means that the magnetic force on it would point to the left. But that's all right because the magnetic field vector points to the left. So anyway, we were left with the question of how to write down a mathematical expression that would produce results consistent with these experimental observations. And at the end of things, I rotated the drawing by 90 degrees. Basically, I took everything and I rotated it 90 degrees into the board. And I'm going to draw that. I'm going to draw that picture here. Choose whichever drawing you like, whichever one makes more sense to you. The results are the same in any case. So I have my little charge. I'm going to, basically in this drawing, I'm going to leave out everything except the vectors. And in a sense, it's going to be a free body diagram. Not quite, though, because I'm going to have a velocity vector. Okay, so if I rotate things 90 degrees into the board, so the velocity was originally pointing this way. Now I'm going to have it point into the board, like so. That's velocity. Our magnetic field was pointing into the board. Now it's going to be pointing straight downward. Our force vector direction, of course, is unaffected. And so that's like that. Okay, again, these two diagrams are equivalent. This is just rotated inward by 90 degrees. Okay. Well, it might occur to you, hopefully it occurred to you while you were thinking about it from the last recording to when you started this one, that the mathematical operation that would rather neatly explain these directions anyway is the cross product. And so now I'm just going to jump right to it. Here comes the mathematical expression. The magnetic force on our test charge Q, due to the fact that it is moving through the magnetic field created by that current, is calculated by F sub B for magnetic force is Q times V cross B. So, some things to notice. First of all, the magnitude of the magnetic force depends on things that you might have guessed. The bigger the charge that you send flying through the magnetic field, the bigger force it's experienced. Think about that for a few moments, convince yourself that's reasonable. The faster our test charge is moving, the bigger the magnetic force. That's less obvious, but it turns out to be the case. Okay? As we learn more about the electric force and field, that will make more sense. And this, I hope, is super reasonable. The stronger the magnetic field that our current creates, the stronger the magnetic force that the test charge feels. Okay? This particular analysis, and I'll come back to the cross product in a moment, but this particular analysis was first done by, I want to say he was German, but I'm not certain. That might have been English. Anyway, yeah, I'm pretty sure it was German. Anyway, a physicist named Lorentz in the mid-1800s or so, early mid-1800s. He actually, so this is, first of all, the magnetic force law. Four-point charge. I will tell you that this particular expression is primarily of pedagogical value. It is, no, that's not true. That's not true. Let me withdraw that statement. It turns out, actually, in light of experiments that have been done in just the last 5 years or so, actually, this particular equation is incredibly important. What I was going to say is that this is primarily a pedagogical value and it isn't used in the real world, quote unquote, all that much, but that was only true until particle accelerators really became super important, in which case, at which point this particular equation is of crucial importance. And in fact, one of the things I'm going to do in this lecture is derive the force function and the force relationship that all particle accelerators, including the one that discovered the Higgs boson over at CERN, the Large Hadron Collider. I'm going to derive for you the mathematical expression that underlies the theory upon which all such particle accelerators are built. Okay, so Q is the magnitude of the charge that you are shooting through the magnetic field. B is the magnetic field that's created by the source current. So B comes from the wire, or more correctly, the current in the wire, whereas Q is a test charge that you're shooting past the wire. Pretty soon, we're going to drop the test charge just as we eventually dropped it when we were considering electric fields versus electric forces. V is the speed of that moving test charge, and so F is the force that that charge will experience. If there happens to be an electric field around as well as this magnetic field, then by superposition you can simply add those two forces together. Okay. Then, so if you have, along with this magnetic field, if you also have an electric field created somehow, and frankly, that's simply the fact that you've got charges moving through a wire, that those charges, moving or not, will have an electric field. Okay. And the net force simply becomes the magnetic force. Now let me say the electric force first. The electric force plus the magnetic force. The electric force is just gotten from Coulomb's law. All right, and so the net force here, just F, is Q times E plus Q times V cross B, or more succinctly, well, actually, yeah, F sub B is this, F sub B is that, or oftentimes it's written as E plus V cross B. And that expression there was the one that Lorentz came up with, and this is known in his honor as the Lorentz force law. Okay. All right. Most of the stuff is pretty straightforward. Working our way through it, most of this stuff you have, in order to actually solve a problem, you have to be told. If your, for example, your test charge is a proton, that by implication tells you that the charge that you're going to insert there is 1.602 times 10 to the minus 19 coulombs. You need to be told enough information to either you need to be told what the electric field is, newtons per coulomb or volts per meter, or whatever the electric field is expressed as, or you have to be given enough information to be able to calculate that field. And then V and B, well, V is something that's typically given to you. And right now, I've told you nothing at all about how we might calculate B. I will do so eventually. But for now, typically you're given B. It turns out that it's not difficult to measure an electric field. There are actually magnetic field sensors. We actually have some in our lab that you'll be working with. So B is pretty easy to measure. Electric field is pretty easy to measure, or perhaps you're given a mathematical expression for those. But whatever you're given, you have to be given them, or have enough information to calculate them, so you can shove them into this equation, and that gives you the force. So that's fairly straightforward. But the thing I want to draw your attention to now, the thing I want to discuss right now, is this cross product. I'm going to assume that you have studied the cross product somewhere back in your past. I'm also going to assume that it's not super duper clear. Okay, so I'm going to briefly go over the cross product, but I'm going to do it in a separate recording. And so, if you are an expert on the cross product, and if it poses no problems for you, whatever, then you should probably still watch the recording anyway. But if you're a little hazy on the cross product, how that works, how you calculate the direction of the resulting vector, and so on, I encourage you to watch the recording on that specifically.